Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. We are now moving to the Module 5, Alcohols and Ethers. So in the lecture 1, we will be studying about properties and general preparation methods for the alcohol. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that we will be covering in this particular session include general properties of alcohols, general method of preparation of alcohols. Mainly we will be focusing on some of the general reduction methods, and we will also be doing a comparison between different reduction methods. So these are all the topics we will be covering in this particular session.
In this lecture, we will see about functional groups, mainly alcohols. So we'll just start with the simplest known hydroxy derivative. Alcohols are generally hydroxy derivatives, ROH, but the simplest one, instead of R, if you put H, it becomes water. So what is the structure of water? From that we will go to the alcohols. So the bond angle, HOH bond angle is 104 degree and the OH distance is 0.96 angstrom. And if you look at methyl alcohol, the simplest alcohol, again the COH, the bond angle is little bit larger than the simple water molecule. So it is 108 degree, 9 minutes, and the distance O and H distance remains the same, 0.96 angstrom, but the CO distance is 1.4 angstrom. So this is the simplest alcohol we know. The oxygen is actually sp3 hybridized. So we have multiple types of alcohols. Let us see what are all the different types. Now I will ask you to identify the different types of alcohols which appear in the screen. Just look carefully. So now we have 4 different compounds which are having hydroxy functionality in this compound. So let us see what is the first one. Okay, now we have 4 different hydroxy derivatives. You have to find out which one is what. This is a primary alcohol. This is a tertiary alcohol. And this is a phenol. And the last one is a secondary alcohol. So how do we define which one is what? So basically, if the hydroxy group is attached to 2 hydrogen containing carbon, that is CH2OH, then that is called a primary alcohol. Then we come to the secondary alcohol. So here the hydroxyl is attached to the carbon which is attached to 1 hydrogen. And when we go to tertiary alcohol, this hydrogen is attached to the carbon which does not have a hydrogen attached to this one. And in the phenol is a hydroxy compound attached to the aromatic ring. So these are the different types of hydroxy or the alcohols available. And if you look at physical properties, they are having high boiling point compared to similar alkanes. The reason is the water molecules and the alcohols all can form hydrogen bonding. So the hydrogen bonding actually increases the boiling point of the substance. And secondly, the small alcohols, methanol, ethanol, propanol, isopropanol. So all these lower hydroxy derivatives, that is alcohols, are water soluble, whereas the higher ones are not. If we look at this table, we know the first four are freely miscible with water, that is they are water soluble, whereas when we go to the higher alcohols, say for example N-hexanol, that is only 0.6% soluble in water. The water molecule actually forms a hydrogen bonding with the alcohol's OH group. The hydrogen forms a hydrogen bonding with this oxygen. Another hydrogen forms a hydrogen bonding with this oxygen. Like that, they both can form two types of hydrogen bonding, and the hydroxyl of the alcohol can form a hydrogen bonding with another water molecule. So this is how they form the multiple hydrogen bondings. That increases the solubility of those alcohols in water. And if we look at acidity of alcohols, they actually range from 15 to 18. That is, they are very close to neutral. That is, water's pKa is 15.7, and alcohols also have the pKa which is very close to water. So that is the reason mainly alcohols are neutral. The acidity actually decreases as the alkyl group size increases, and if any substituent is present, especially halogens, they increase the acidity. And if we look at aromatic one, that is the phenol, is 100 million times more acidic than simple cyclohexanol. Say for example, in this you will see cyclohexanol and phenol. The phenol is highly acidic compared to the cyclohexanol. And the next one, what we can say is why alcohols are important. Because alcohols can be used in the conversion of various different compounds. So one such reaction is formation of alkoxide. So when an alcohol is treated with a metal, basically sodium, it forms the sodium alkoxide with the liberation of hydrogen. This is an irreversible reaction because the reaction produces hydrogen which escapes. So that means it is an irreversible reaction. And strongly acidic alcohols require a weak base or a weak metal, whereas less acidic alcohols require a highly reactive metals, basically sodium, potassium. For example, if we take ethanol is quite highly reactive, so to make an alkoxide we only require sodium, which is a less reactive metal. In the case of tertiary butanol, which is very less acidic, we need a stronger base, that is the potassium is required to make the alkoxide ion.
Let us start our synthesis of alcohols. Before we delve into the complete synthesis procedures, we will just look at a few of the important points that we will have to remember or in understanding how the whole synthesis can be categorized in a very simple way. We have two major types. One is from carbonyl compounds. That means alcohols can be synthesized from carbonyl compounds, or they can be synthesized from compounds other than carbonyls. So these are all the two major categories which we can divide the entire synthesis of alcohols. And under the synthesis of carbonyl compounds, we again have two major types. One is there is no change in the number of carbon atoms. That means the carbon atom skeleton remains the same from the carbonyl compound and the alcohols. And there are another type where there is a change in carbon numbers. In other words, the carbonyl compound and the alcohol obtained will have a different number of carbon atoms. So these are all the two major types which we will be briefly looking at right now. Under the case of no change in carbon atoms, we have a major class of reaction called reduction reactions. So the reduction of, this is the ketones, aldehydes. So ketone or aldehyde reduction leads to alcohols with the same number of carbon atoms, or esters and carboxylic acids. When we do the reduction, we will be having the same number of carbon atoms. So these are all the different types of reduction methods of carbonyl compounds which leads to the alcohol which are having the same number of carbon atoms. Let us look at some of the examples briefly. One is aldehyde when reduced with sodium borohydride gives a primary alcohol. So in this case the number of carbon atoms remains the same. There is no change in the number of carbon atoms. And the ketone when reduced using lithium aluminium hydride or aluminium isopropoxide or even sodium borohydride. So all these three reagents can be used for the reduction of carbonyl compounds, especially ketones, gives a secondary alcohol with the same number of carbon atoms. There is no change in the number of carbon atoms. The carboxylic acids can be reduced using borane to give the corresponding primary alcohols. And LAH cannot be used, or lithium aluminum hydride cannot be used in this particular case, whereas borane can be used to reduce carboxylic acid to corresponding primary alcohols. So these are all the various methods. Aldehydes, ketones and can be reduced using the shown reducing agent to give either primary or secondary alcohols. In all these cases, the number of carbon atoms in the starting aldehyde or the starting ketone to the alcohol remains the same. Then let us look at the change in number of carbon atoms from the carbonyl compound to the alcohol synthesis. So the major reaction what we will be studying under here is the Grignard reaction. We have formaldehyde as one of the component. This gives the primary alcohols, and the other one is starting material is any aldehyde that gives secondary alcohols. We have esters, acid chlorides and ketones that gives the tertiary alcohols. So these are all the different carbonyl compounds which can be employed to synthesize alcohols using Grignard reaction. So let us look at the Grignard reaction briefly. So formaldehyde reacts with the RMgX to give primary alcohols. Aldehydes, only formaldehyde gives the primary alcohol. Any other aldehyde with the reaction with the Grignard reagent gives the secondary alcohol. Ketones or esters, when they are subject to Grignard reaction, produces tertiary alcohol. So in all these cases, the number of carbon atoms changes from the aldehyde or the ketone. The carbonyl starting material and the obtained alcohol will have different number of carbon atoms. So this is where we say the change in the carbon numbers occurs. Okay, and next we will be looking at compounds other than carbonyl compounds. So here also we have two major types. One is no change in the number of carbon atoms, another one is change in the number of carbon atoms. So these are all the two again major categories by which carbonyl compounds other than carbonyls can be used to synthesize alcohol. In the first one, no change in carbon compounds, the groups other than carbonyls, we have hydrolysis reaction. That means alkyl halides can be hydrolyzed to produce alcohols with the same number of carbon atoms. And we also have a hydration reaction. That means alkenes can be converted into alcohols with the same number of carbon atoms. There are two major reactions we will be studying. One is mercuration, demercuration, that is use of mercuric acetate and sodium borohydride to give the alcohols. This follows Markovnikov addition principles. And the second one is the hydroboration reaction. This follows anti-Markovnikov addition. So these are all the two major methods of conversion of alkenes to alcohols. In this particular case, the number of carbon atoms remain the same. And when we talk about change in number of carbon atoms, we again have the same reaction similar to Grignard reaction. So here the alkyl halide can be converted into Grignard reagent that can be reacted with the carbonyl compound to produce alcohols. So these are all the overall methods of different methods of synthesis of alcohols. Let us look at methods of synthesis of alcohols one by one. What are the different types we will be studying in this particular case? The first one is oxymercuration and demercuration reaction. The next one is hydroboration and oxidation reaction. The next one is the Grignard reaction. The next one is hydrolysis of alkyl halides and aldol condensation or aldol reaction, reduction of carbonyl compounds, reduction of acids and esters, hydroxylation of alkenes. So these are all the different methods, individual methods, which we will be studying in this particular session and the next session also. So here the overall reaction for the mercuric acetate is given. So Hg2 plus ion is the electrophile in this particular reaction. This alkene reacted with the mercuric sulfate and water gives the corresponding hydroxy derivative with mercuric acetate present, and the reduction of this using sodium borohydride removes the mercuric acetate HgOAc part and it introduces the hydrate because it's a hydrate reducing agent. So this group is substituted with the help of the hydrate to give the corresponding hydroxy compound, that is alcohol, and this reaction follows Markovnikov addition. And in this case we have a cyclic intermediate that is formed. Before the hydroxyl is introduced, this carbon and mercury are in the +2 oxidation state with the electrophile being the Hg2 plus ion. So due to this there is no rearrangement possible in this particular reaction. We do not have a separate carbocation formed in this reaction. So this intermediate was attacked by the hydroxide anion. So this opens up to produce this particular derivative. And when we use substituted alkenes as shown here, this carbon has a methyl group and a hydrogen. This carbon has hydrogen and hydrogen, only 2 hydrogens. So this is a substituted carbon. When this undergoes oxymercuration, demercuration reaction, the hydroxy group is introduced to the substituted carbon. So this is why this is called a Markovnikov addition. Then we have hydroboration oxidation reaction. This reaction actually follows anti-Markovnikov addition, as we have mentioned. We take the same alkene and treat it with the borane reagent, and this forms the additive compound, which on treatment with the hydrogen peroxide in the presence of a hydroxide base produces the alcohol. The hydroxyl group is attached to the least substituted carbon, so this follows anti-Markovnikov addition. So oxymercuration and demercuration reaction and hydroboration oxidation reaction are complementary to each other. One follows Markovnikov addition, the other one follows anti-Markovnikov addition, so that both the type of hydroxy compounds, that is alcohols, can be produced from alkenes. Let us look at reduction using sodium borohydride. In this particular case, an aldehyde is treated with the sodium borohydride to produce the corresponding alcohol. So when we look at the mechanism, what happens is the hydride, sodium borohydride is given here, Na is plus and the borohydride is having minus charge. So this hydride ion is transferred to the electropositive carbonyl carbon, and this double bond electrons are shifted towards the most electronegative oxygen. So that produces the intermediate of the anion is produced as shown here, and this abstracts a proton from the solvent molecule to produce the corresponding alcohol as the final product. And the first step is what is called the addition reaction. So the addition of the hydride takes place in the first step, and in the second step it is the protonation reaction of the corresponding anion that is formed. and these are all the two reactions, and this protonation reaction is a very fast and the facile reaction. In the previous case, what we have seen is we have used a protic solvent, that is water is used as a solvent. If there is no protic solvent, that is if an aprotic solvent is used, like for example DMF, the reaction mechanism is little different than the previous one. So in this particular case, what happens is the borohydride ion, the hydride is still added to the same carbonyl carbon, which is electron deficient, and this double bond is now formed to the boron. Not the oxygen is this bond is not shifted towards oxygen, but it is bonded to boron. So this kind of an intermediate is formed in the first step. So this boron has 1, 2, 3. So there are 3 more hydrogens are there. So every hydrogen is replaced by the corresponding carbonyl compound. So we have a tetra substituted boron with the oxygen bond, and this compound now undergoes acidic workup to produce 4 molecules of the corresponding alcohol. So this is how the reaction proceeds in an aprotic solvent where DMF is used as a solvent. So the reaction mechanism differs from the protic solvent case. In the protic solvent, this particular step, the oxygen takes the negative charge in the first step addition. When the hydride is added in the first step, second step is simply the protonation of this intermediate. But in the case of DMF, an aprotic solvent, the reaction proceeds through a different mechanism. And let us look at the next one, which is the reduction of carbonyl compounds using lithium aluminium hydride. In this particular case, we will first look at the ester reduction. So here, like sodium borohydride, aluminium hydride is also transferring the hydride. In this particular case, the nucleophile is the hydride ion. This adds to the electrophilic carbon of the carbonyl group, and this oxygen, the double bond is shifted towards the more electronegative oxygen, and this oxygen is actually coordinated with the lithium plus ion from the lithium aluminium hydride. And in the second step, what happens is like the negative charge on oxygen is charge reversal happens, and it comes between the carbon oxygen bond with the concomitant removal of the OR minus. The alkoxide is removed in this particular step. So we end up with an aldehyde. That is the first step. So the first reduction of the ester gives aldehyde, and this again one more times undergoes reduction using lithium aluminium hydride. So this time another hydride ion is added to the electropositive carbon atom, and the oxygen, the double bond is shifted towards the most electronegative oxygen, and this produces the oxide anion in this particular case, and this undergoes protonation to give the corresponding alcohol. So this can be considered as a two-step procedure, but of course we do not isolate the aldehyde in this particular reaction. When we run the reaction, we start with the ester and we directly end up with the corresponding alcohol. The aldehyde intermediate is not generally isolated. Now the biggest question what we have in our mind is why sodium borohydride reacts differently with LiAlH4 or lithium aluminium hydride, because we already know sodium borohydride reduces carbonyls, especially ketones and aldehydes, but it does not reduce esters, whereas lithium aluminium hydride can reduce esters. So there is a different reactivity, even though hydride ion is the one which is involved in both the reduction. So we need to find out what is the reason behind the different reactivity of sodium borohydride and lithium aluminium hydride. So we have some explanation here. Let us look at basically the electronic configuration of boron and aluminium, because in this particular case we have the central atom which is boron in sodium borohydride and aluminium in lithium aluminium hydride. So the boron's electronic configuration and aluminium's electronic configurations are written here. It is 2s2 2p1 for the boron, and for aluminium it is 3s2 3p1. So they are one row below. Boron is at the top, aluminium is at the second row. So when we look at the size, boron is smaller in size, whereas aluminium is a little bit larger in size. And when we compare the electronegativity of boron is very high, 2.04 compared to aluminium, which is 1.61. So this is one of the reason. We will just find out what is the electronegativity has to do with the reduction. And if you look at the XH bond length, the bond length is very short because it is more electronegative. So that's the reason the bond length here is very short, whereas in the case of aluminium, the aluminium hydrogen bond length is 1.61 angstrom. It is a little bit longer. So in other words, when the bonds are shorter, they are going to be strong. That's the reason the XH bond, that is boron hydrogen bond, is strong, whereas aluminium hydrogen bond is very weak. And due to this, if you look at the bond reactivity, when the bond is very strong, obviously they are less reactive because they cannot be broken down very easily, whereas when the bond is very weak, they are very easily cleaved. So that is the reason they are highly reactive. So if we compare between the electronegativity and the bond strength, what we can conclude is the low electronegativity of aluminium than the boron basically shifts the electron density towards the hydrogen on ALH bond. That means the electron density on hydrogen is more compared to aluminium in the case of ALH bond, whereas in the BH bond it is not that much different. So the lithium aluminum hydride is a better hydride donor because it has a very weak ALH bond. So this is the reason the aluminum hydride is a better reducing agent than borohydride, sodium borohydride. Let us look at some of the comparison between the reactivity among boron reducing agents. So we have sodium borohydride as our reference, and we have lithium borohydride, sodium cyanoborohydride, sodium triacetoxy borohydride, and borane. So these are all the different boron reducing agents, and lithium borohydride is stronger than sodium borohydride, whereas sodium cyanoborohydride and triacetoxy borohydride are milder than sodium borohydride. Borane is stronger than sodium borohydride. So why do we need to have different type of reducing agents? Because these different reducing agents can be used for chemoselective reduction of carbonyl groups. Say for example, we have a ketone and an aldehyde and an ester in a compound, and we want to selectively reduce the aldehyde only, then we can actually choose the right reducing agent to selectively reduce the aldehyde alone. So when we talk about the reducing power, sodium borohydride can reduce imines, aldehydes and ketones, whereas lithium borohydride can reduce even esters. So if we have a comparison between sodium borohydride and lithium borohydride is a much stronger reducing agent than sodium borohydride. And the reason for this is like the lithium can actually complex with the carbonyl oxygen and of the ester group. So this helps in the reduction of esters. So that is what is the reason. The complexation of lithium with the oxygen is very crucial for the reduction of ester groups using lithium borohydride. And when we talk about sodium cyanoborohydride, this only reduces imine. And sodium triacetoxy borohydride, this reduces imine aldehydes but not ketones. So as I mentioned, the selectivity, sodium borohydride can reduce imine, aldehyde and ketones, whereas triacetoxy borohydride can reduce imine and aldehyde, but it will not reduce ketones. And when we take about the borane, so borane does not, of course, reduces aldehydes and ketone very slowly, but it reduces amide and acids much better. So whereas sodium borohydride does not reduce amides and acids. So when we have different type of carbonyl compounds, we can selectively choose one of the reducing agent to reduce the corresponding carbonyl groups. And of course, when we talk about the reactivity in a protic solvent, sodium borohydride reacts very slowly in a protic solvent. Sodium cyanoborohydride reacts with methanol but not reacts with other alcohols. And sodium triacetoxy borohydride, it hydrolyzes very readily. So that is the reason it is not used in alcoholic solvents. So when we choose the solvent for the reaction, it is very crucial that the reducing agent should not react with the solvent. And here is a complete comparison chart of reactivity of various reducing agents. So the first one is the milder one, which is the sodium cyanoborohydride, followed by sodium triacetoxyborohydride, then sodium borohydride, cerium chloride in sodium borohydride. This is called Lucci reduction or Lucci reagent. And we have lithium borohydride, borane, diisobutyl aluminium hydride, and lithium aluminum hydride, which is the most stronger reducing agent. So if we go from a different functional group, imines, aldehydes, ketones, esters, amides, carboxylic acids, alkenes, alpha beta unsaturated aldehydes, and acid chloride. So we have various functional groups that are present, and we have various reducing agents that are present. So we can choose the corresponding reducing agent to reduce selectively one of the functional group. Say for example, if you want to reduce the imine, we can use any of this except the dibal. We can use any reducing agent for this particular reduction. But when we talk about aldehydes, use of sodium cyanoborohydride, it is very slow, not very fast. The same way borane also cannot be used for the reduction of aldehyde because that reaction is very slow. But when we use cerium chloride in sodium borohydride, it does not reduce aldehyde. So this is one of the very crucial development between sodium borohydride and the use of cerium salt. So if we use simple sodium borohydride, this reduces imines, aldehydes and ketones. All the three are reduced. Whereas when we use cerium chloride and the sodium borohydride combination, it does not reduce aldehyde. So that means if we have a ketone and an aldehyde, we can actually choose the same reducing agent sodium borohydride with the cerium chloride to selectively reduce the ketone, whereas aldehyde is not affected. So this is how we can actually choose the right set of reducing agent for reducing a particular functionality. And when we take about the ketones, sodium triacetoxyborohydride does not reduce it. So in other words, if we have to selectively reduce an aldehyde and a ketone, we can use this particular reagent. And if we have to reduce only ketone and not aldehyde, we can use this reagent. So chemoselectivity can be very well addressed with the help of differing reducing agents. And if we take esters, sodium borohydride or sodium triacetoxyborohydride or sodium cyanoborohydride or cerium chloride and sodium borohydride, none of them reduces the ester group, whereas lithium borohydride reduces very efficiently. Dibal and dibal H and lithium aluminum hydride both reduce esters. And when we take about amides, dibal H and lithium aluminum hydride are the best reducing agents for the reduction of amides. And for the carboxylic acid, borane is the only thing which works very efficiently, whereas lithium aluminum hydride and dibal H reduces the carboxylic acid very slowly. And when we take about alkene, borane actually reacts with the alkene, whereas dibal H, the terminal double bonds are reduced. So for the alkene reduction, we generally use palladium or platinum or nickel in the presence of hydrogen is used for reducing double bonds, whereas none of the boron reducing agents which we had shown here reduces the alkene except the dibal H, which reduces only the terminal double bond. And when we talk about alpha beta unsaturated carbonyl compound, dibal H and lithium aluminum hydride can reduce the alpha beta unsaturated hydrogen carbon. So here the green color means the particular functional group is reduced, and orange means they are slowly reduced, red means they are not at all reduced, and blue and yellow are basically, the yellow means it reacts with the particular functional group, blue means only the terminal double bonds are reduced. And when we take the acid chloride, sodium borohydride and many other reducing agents reduce the acid chloride, whereas borane and dibal H does not reduce the acid chloride. So this is how, by using this chart, we can actually choose the right reducing agent for reducing a particular functional group. In summary, to recap what we have studied so far, we have studied various general properties of alcohol, that is why alcohols are highly soluble, lower alcohols are highly soluble in water due to hydrogen bonding. And we also have studied about the general methods of preparation of alcohols, mainly from carbonyl compounds and non-carbonyl compounds at starting materials having the same number of carbon atoms and different number of carbon atoms. So all those methods, general methods we have seen, and we have also studied about the various reduction methods using different reducing agents. And we also have studied about the comparison between sodium borohydride and lithium aluminium hydride, why one is milder and another one is stronger reducing agent. And we also studied about the comparison between different boron reagents, so how these can be employed to reduce various alcohol esters or acid chlorides or ketones or aldehydes, how chemoselectivity can be obtained using different reducing agents also we have studied. With that, we conclude this session. Thank you.